Alright, today I will talk about the problem fencing the cows. So in this problem, what we want to do is find out a few points so then we can connect a few lines and then all of the other points will be enclosed inside those lines. And so this is the convex hull problem. And the reason it's called convex hull is that the optimal solution is guaranteed to definitely not be any concave shapes, because for example here, let's say we have these few points, and if we connect a fence toward this point to this point, and then connect this point to this point, we did wrap up everything, and everything inside will be included. But instead of doing this, which forms a concave shape, we can just connect the line from this point to this point, and this way we'll get a shorter length than connecting these two. So overall, the whole thing will be always a convex shape. And to do that, we will use a few math stuff. The first thing required for this is using the vector to get the cross product, and also the other thing that you need is to calculate the angles of each of these points. So first, here I will read in the points, and while reading the points, which I created as a structure here, I also created a z variable. Also, we don't need that here, but I did this to show you what a normal cross product will be like. So first, we will out of all of these points, we want to find the point with the minimum y. And if there's a tie with the minimum y, then we will find the one with the smallest x. And so if you think about this, what this does is that it gets the points that is at the most bottom. And if there are multiple points that are at the most bottom, we will find one that is at the most bottom left. So after doing this, we will be able to think of this as the origin, and then we can calculate the angles for each of these points. So to get the angles, we will get the change in y and change in x for each of these points in comparison with our origin, which we found here by comparing the minimum y and minimum x. So to get the angle, we know that tangent is basically the change in y divided by the change in x. So you can use arctangent to get the angle for this. And here you should use arctangent 2 instead of just the normal arctangent, because arctangent 2 will also take care of the case if the change in x was 0. If basically meaning that if you have 2 points that are on the same horizontal line, or or basically on the same vertical line. And also here you also push back the index, because we will sort this list of degrees over here, so then we can get the points in order, sort of like wrapping around the whole shape. And so we will sort this, and we'll look at all the points in this current shape that we sorted on. So first of all, this will be our answer vector outside. I will first push in the point from the origin, because we know that this point is at the most bottom. That means that this point will definitely be included inside this convex hull shape. So we will push that back into the answer vector, and also we'll push another one back, and this point will give us the smallest. This is the smallest. This is the one that has the smallest angle inside our sorted angle list for each of these points. And we do this because when it has the smallest angle, this means that it's basically the one that is at the nearest of this first point. So we will push this point into this as well. And here we will just loop through all of our sorted points. But here at the end, I also pushed back this our origin point, because we want to go all the way around and back to the starting point to wrap around the whole thing. So here we'll get the point that we're currently looking for, and this will go in order of the angle. So here we will get the cross product, and this is basically our first 2 points, our last 2 points that we got. And so this is why I pushed in this point as well, because we will think of this as a middle point. So every time we do this, we will compare what happens if we connect the previous point, which is this point, with this current point. And we do this because then we'll be able to check for any cases like this, where, for example, if we search this point as the origin, but of course this one should be the origin here, but let's say we're at this point, and we search this point, so these 2 points are currently in the vector list, and we're looking at this point now. So here we will look at this point as well and this point to get their orientation, so we will know whether they are concave or convex. And so this is what the cross product do. This will make sure that we are always having a convex shape. So here I will create 2 vectors, but here this isn't a vector in the C++ data structure. This is a vector that represents magnitudes, mass. So here this will be the 2 points, and we will have a few magnitudes, the x magnitude, the y, and the z. But here the z, of course, will first remain as 0. And so to get these magnitudes, you just find the difference between those 2 points. And in here we'll use this cross product to find the orientations of those points. So we'll have first one vector and another vector, and we will by getting the cross product, we will do this. So first we will multiply the y value for the y magnitude for the first vector by the z magnitude of the second vector, and then subtract it by the other way around. And for the second one, we will do the z magnitude of this first vector multiplied by the x magnitude of the second one, and also subtract it with the other way around. The u for the first one, we'll get the x magnitude and multiply that by the z magnitude for the second one. And then to the third one, we will get the x magnitude of the first one and multiply it by the y in the second one, and then subtract it by the y in the first one and x in the second one. So finally, this cross product vector will be just those 3 values. And here, how we will check for the orientation is that since we know that our z here at the beginning, they're just all 0 because we don't have a z value here. So these 2 I and j will just remain as 0. And this k will have a value, which is the first x value multiplied by the next y value, and subtracted from the first y value multiplied by the second x value. So here, what this returns will first just be 0, 0, and then the value k. So this k will be our z value for this new vector. And so this is what we will compare. We will get the z value here. And also when we multiply the 2 vectors, we're actually getting the vector for the last 2 points and the vector of the last point and this current point. So this will check for its orientation. If this current z is smaller than 0, this will mean that we formed a clockwise orientation. And if it's equal to 0, this means that they're on the same line. So we don't want any of those cases. For example, here, right now, if we are looking at these 3 points, then these 3 actually form a clockwise orientation because it goes from here to here, and then you can just imagine it going all the way around in this direction. So since we're searching like this way, we're going first here, finding the next value, and then going this way. We're always looking for a counterclockwise orientation. Think of these points as going in this direction. So if they're in this clockwise direction, we will remove this current point and just push this point back into our answer vector list. And the other case is when they're on the same line, and I removed this as well. Also, you can still keep it because the value will still be the same. You just get the distance from here to this point and from this point to this point. But I just removed this to 2 because this can also be useless since you can just get the distance from all the way from this point to this point. So just remove any case where we form a counterclock, where we form a clockwise orientation, or a link, or just the few points are in the same line. And we also have to make sure that our current answer is bigger than 1 because we have to do the cross product again for the next one. And so if it's that case, then we'll pop back the previous value, the previous point, and here we'll just do this again. Just keep on doing this until there are no more until there are no more clockwise orientations, and then finally we can push this this current point back into our answer vector. And then here, this was the part where we'll finally calculate the length. So the total length required can also be calculated using vectors. And so how we can do that is just by creating these 2 points, which are the few points that are adjacent to each other in our answer list. So we'll get the vector for those 2 points, and then just get the length of that. And to get the length of that, we'll just do the square root of each of these different magnitudes squared plus adding together. And so this is basically the same thing as Pythagorean theorem. Just getting the length and adding that to our count. Also, we have to remember that since we need to go all the way around and connect this the final point to the first point, so this is what this does here. We'll connect the first point with the final point. And here I didn't loop all the way to the end of this answer size. I did -1 because here, this is why we push this back. We push this first point into the end of our sorted point list, because then at the end we'll be able to check for any final concave shapes, and we can remove all of those points as well and connect our first point to the next point. So here at the end, we'll push back our first point again, and we don't need to print out we don't need to check our first point 2 times. So we just have to do the ones. We just have to check for the ones that are one before our final answer, which is the first point. So here, finally, just adding the distance from the first point to the last point, and then you can print out the final complete length with also a decimal precision of 2.